Welcome to lecture 3 of week 2. This will be our final lecture for this week. This is all about plate boundaries and seafloor features. So we're just going to get more into those plate boundaries that I introduced in the last lecture. So plate boundaries are where plates meet at the Earth's surface and they tend to change the surface of the Earth. They tend to change the shape of the Earth. The edges are some of the most dynamic and fascinating places on Earth. They form ridges, trenches, faults, volcanoes, earthquakes happen in these areas. There's just a lot happening. The geology is really dynamic in these areas. The seafloor really does tell the story of plate motion over time. It gives us a detailed record of how the plates have moved over time. By understanding all of this, we can actually read Earth's history. It's almost like a history book of what's happened on the seafloor and at any of those plate boundaries. So let's go ahead and just look at there are some smaller plates that aren't listed on this map. This map is all the main, larger tectonic plates. So if we want to find a spot, so first we've already talked about the Hawaii being in the middle of the Pacific Plate. The Pacific Plate is one of, if not the biggest tectonic plate. And we are right smack dab in the middle of it on a hot spot. So even though we're sitting on a volcano and we get earthquakes all the time, we're actually not at the edge of a plate, we're on a hot spot. We can see here, California has a lot of earthquake activity, and even Mount St. Helens blew up many years ago because it is on the boundary of a plate that's trying to move and change, and that's what's causing a lot of that action in California. So I'm just going to talk about those two, but you will see this map again. We'll look at it for different things, and anytime that you start to get confused about plates or you're looking at too many and something gets too much, pull up this diagram because it is an easy one to just see where things are, and this colored one makes it nice and easy to read. So we'll start with divergent boundaries, where plates are moving apart. In a divergent boundary, two tectonic plates are moving away from each other, and generally magma rises to form new crust there. So it's going to fill that gap. So if it's an ocean divergent boundary, we're essentially building more ocean that way. This is where mid-ocean ridges occur, and it's where rift valleys can occur. So the Mid-Atlantic Ridge is a great example of this. Iceland actually sits right on top of this ridge, so you can stand on two different plates at once in certain parts of Iceland. And on land, an example is the East African Rift Valley, where the African continent is essentially splitting into two plates. And one day there will likely be ocean there because they're going to pull apart over time. If plates pull apart in some places, they have to collide in others because the Earth isn't actually getting bigger, it's staying the same size. So if two plates are spreading apart here, that means others have to be colliding somewhere else and moving in together. Oh, first we're looking at the Iceland plate here that I was just talking about. So you can see in Iceland, you can see that these two plates are pulling apart, and we've got volcanoes along here. So interesting. If anybody's ever been to Iceland, I'd love to hear if you went there and saw any of this. So then where plates come together. So convergent boundaries are two plates are going to be colliding. And depending on what types of crust meet, different things can happen. So one essentially always has to sink under the other. When there's an ocean plate involved, one has to sink under the other. So if it's an ocean continental plate, so one's land and one is ocean, the ocean is going to subduct or sink underneath of the continental crust because that ocean crust is more dense. Remember, the more dense plate will always be the one that sinks. So this causes subduction zones and trenches like the Mariana Trench. If it's two continental plates colliding, neither one wants to sink. And so a lot of times what happens is we get big mountain chains forming. So when we get big mountain chains, that's usually formed by two plates converging, come together. When it's ocean crust, one plate has to subduct beneath the other. And a lot of times what will happen is an island arc will form. So the Mariana Islands, that is an ocean convergent boundary. And here's an example where we have oceanic crust and continental crust converging together, and the ocean crust subducts underneath of the continental crust. And in this case, we have ocean crust coming together. And in this case, this part of ocean crust is more dense, and so it subducts underneath. And we get a volcano forming here as well. Not always, but a lot of times. Transform boundaries are where plates slide past each other. So this one is a little bit harder to understand, I think, but if some plates are crashing together and some are pulling apart, there are going to be other spots where plates end up sliding past each other, or parts of plates slide past each other, and that doesn't happen easily. So these things grind past each other, and crust isn't created or destroyed, but it makes fault lines, like the San Andreas Fault, the Queen Charlotte Fault. These are areas where that crust is just sliding past each other. A lot of times it causes earthquakes. And it's very slow, only a few centimeters a year, but it adds up over time and causes these faults. Here in Hawaii, we can see a transform fault cutting across the Pacific seafloor, and it looks like zigzaggy patterns around the mid-ocean ridges. It's not something we see just by looking, but if we look at maps and bathymetric maps, we can see that. Let's just kind of talk now about how those movements shape the overall structure of the ocean floor. So here we're looking again at the San Andreas Fault and the transform boundary real quick before we move on and look at how everything shapes. But I just wanted to show just a little bit of these transform faults. So things that are shaped by the seafloor, by the movement of the seafloor, the continental shelf, the continental slope, and rise. We're going to look at a diagram of that here in just a minute, showing all of those areas. But the continental shelf is going to be an area that's shallow and sloping, where a lot of the coral reefs are found. The slope is going to be a drop off. It's usually pretty steep, and that's what leads to the deep ocean. And then we can have continental rises, where sediments accumulate, and it's essentially the base of a slope. We have abyssal plains, where just flat, deep ocean, there's some of the flattest areas in the entire Earth. We have mid-ocean ridges. We've talked about those a bit already, but those are essentially long underwater mountain chains. We also have trenches that are going to be narrow depressions, like a canyon. And we have seamounts, and those are more like underwater volcanoes. So obviously, those are all important, and they're all caused by plate tectonics crashing together or pulling apart or sliding past each other over time. So you can think about that kind of as a cross-section. And here's our cross-section. So if we're on land, we have the continental shelf. It's very shallow, where a lot of the reefs are. Continental slope. Here's an example of an abyssal plain, where it's nice and flat for a long time. A small abyssal hill. A seamount, a volcanic island. Essentially, a seamount and a volcanic island are the same thing, except one is coming out of the water and one is still underwater. And we have an ocean trench. So again, this is a great diagram to come back to if you can't remember what the continental shelf, continental slope are, things like that. Mapping the seafloor features. So obviously we talked about bathymetry in week 1, and that's, the study and mapping of the seafloor. And to understand all of that, we use bathymetry and map the seafloor using things like sonar, satellites, submersibles that all show us what the seafloor looks like. Even still, the majority of the seafloor remains unmapped. So even though we're working on it, it is still only about 25% mapped in detail. Now, we kind of in general know what's happening at most of the seafloor, but the details are still being figured out. So it's really interesting, and people are constantly working to map the entire seafloor. There's a specific project called Seabed 2030 where they're using sonar and satellite data to attempt to map the entire seafloor by 2030. I don't know if it'll be finished in time or not, but it's interesting. In your virtual lab, in your activity this week, next week, you're going to get to look at these different plates and see how they move and really get a better look at them. I told you you get to see this bathymetric map again, and here it is. So you can see there's a plate boundary right here in the middle of the Atlantic Ocean that is spreading apart, making new crust right in through here. We can look at the coast of California and see a lot of weird things are happening here because we have all those transform faults happening. So again, if you want to compare this map to that colorful plate boundary map that I showed at the beginning, that's a great way to kind of see those plates and how they match up with different features in the ocean. So we've already talked a little bit about Hawaii and the Pacific plate, but the Pacific plate moves northwest over a hotspot. It's almost in the middle of it, and the Big Island is right on top of that hotspot now. Hawaii's volcanic chain records millions of years of motion. So all of the Hawaiian Islands and the Emperor Seamount chain are formed because of that hotspot. The direction, the plate bent about 47 million years ago, and that's the shift where from the Emperor Seamount to the Hawaiian Islands looks different. So if we go back, we can see here's Hawaii now, and you can see the plates moved this way, but then this part of it is a different direction, and that's when the plate did a major shift about 47 million years ago. Okay. So yeah, we get to live in one of the most volcanically active regions in the world, one of the most interesting as far as I'm concerned. And all of these, let's go back one more time. All of these volcanoes and trenches and stuff around the Pacific plate is what's called the Ring of Fire. So that's why it's called that. There's a lot of volcanoes in that area because of that plate. One more look at it. Again, you've seen this image before, but we have the Hawaiian Islands here, the Hawaiian Ridge, all of our Hawaiian Islands, and the Emperor Seamounts here. And you can see a lot of these convergent boundaries around the Pacific plate, causing a lot of volcanoes and other geologically active areas. So as you can see, the seafloor is constantly changing. It's moving. It's almost like a living surface. It's always moving and changing. The new crust forms at ridges. Old crust is recycled at trenches. So it's always changing, even though the Earth stays the same size. So continents and oceans get reshaped over time. They don't stay the same. An example is the Atlantic Ocean is in the young to slightly mature stage because it's expanding as new crust forms. The Pacific Ocean, on the other hand, is actually gradually sinking as it's subducting into the continents. So just an interesting thing to think about. Again, I think I've shown you this slide before, but it's great for studying. You can see divergent boundaries, convergent boundaries, what happens at them, a subducting plate. So come back to some of these diagrams for studying when you need them. Okay, this lecture we talked about convergent boundaries, divergent boundaries, and transform boundaries, and how the ocean floor essentially records activity over time in all of these geologic formations like ridges and trenches. So Hawaii itself is living proof of a moving and changing planet, which again is mind-blowing and super interesting. So this is our final lecture for week 2. So now would be the time to go and do your discussion, question and answer, and your activity, and then your quiz. And again, as always, if you have any questions, let me know. You can start a discussion, you can email me, come to office hours, whatever you need. I am happy to help out, and I will see you in week 3.